Hi, good evening, Venkatesh.
Hi, good evening, Sushma.
Hi, yeah. So I think we can start in another 1 or 2 minutes if you are ready. Yeah.
Sure, yeah. 1 minute.
Okay.
I will.
Okay. Yeah. Sure. Yeah. Take time. Sure.
Hi, I have joined with my another computer. Can you allow me to share screen?
Yeah. Sure. I'll do that.
Yeah, from there. Thanks.
Yeah. I think now you should be able to share. Yeah.
Yeah. Shall I start now or?
I think we can start. Yes.
Okay. So are you able to see my screen properly?
Yes, we can see.
Okay, great. Okay. So yesterday I was actually talking about so what is the important problem in linear algebra about matrix multiplication, and then how we can approach that problem. That is what I was talking about yesterday. So giving some motivation for that problem. Okay. So today actually we will see how one approaches that problem. We will develop some theory and then see like what are all the some general possible methods to approach that problem. So for that, actually, we need to develop some theory. So we need to understand some of the terminologies that is used in linear algebra. So I will actually begin with those things. So yesterday I told I will be actually talking about this change of basis, but I didn't have time to talk about it. But today I will actually start with that and then we will slowly move on. Okay, so now to actually begin, okay, so before getting into change of basis, first let's understand how one can associate a matrix with the given linear map. Okay, so all of you are comfortable with the notion of basis and so on. So that I will just assume. Okay, so now so what we are going to do is actually a matrix of a linear map. So I'm going to do it in some much generality so that it will be actually very useful later, like when we specialize to these linear operators on given finite dimensional space. So how one can associate the matrix? Okay, so that is done as follows. So first, let's fix some finite dimensional vector spaces. Okay, let's call them V and W, and we also fix a linear transformation from V to W. Okay, so V and W, they are finite dimensional vector spaces over some field F. And then So let's fix dimension of these spaces. Let's say the dimension of V is n, and then dimension of W over F, that is m. Okay, so this is fixed. So now what I want to do, I want to start with a linear transformation from V to W. So we have a linear transformation from V to W. So this is given. So now I want to actually associate a matrix with this T. Of course, to do that, we need to actually fix basis of this V and W. Okay, so for that purpose, let's fix a basis. Let me call it V bar. So which is a basis V1, etc. Vn. So this is a basis of V, and W bar, so which I denoted by W, etc. Wm. So because the dimension of W is m, so this is basis of W. So this is something we fix. So now, so what we can do actually, so we can look at. So we want to understand this linear transformation. Okay, so this is the first thing one actually learns in linear algebra. Okay, so if we have a linear transformation that is from V to W, then to understand this linear transformation, it is enough to understand its action on the basis. Okay, so what I mean by that, okay, so here is some small exercise. So T is actually completely determined by, so T is completely determined by its action on this basis V bar. Okay, so that means the values, okay, what is this TV1, etc., TV. So again, to say what is this values TV1, etc., TVN, so we can actually use the basis of W and then write down what they are in terms of this basis WG. Okay, so that is what. So this is something I believe it as exercise. So this is actually follows from the linearity. Okay, so because if you take any vector in V, that vector can be written as some linear combination of these VIs. Okay, for some scalar Ci and F. So in particularly to know what is this T of V, then using linearity of T, we can see that T of V is nothing but summation Ci T of Va. Okay, so to say, so what is T of V? So we need to actually understand what is this T of Vi. And then if we know how to write V in terms of this Vi, basis Vi, then using that information, we can actually calculate what will be the image of T, image of V under T. Okay, so that is why this T linear map is completely determined by its action on this basis V bar. So now to understand this action, what we can do, we can actually look at TVK, and then we can write this TVK as linear combination of this basis WJ. Okay, so then you can actually get some scalars which I denoted by AJK. So this TVK will be equal to summation AJK WJ, where J is running from 1 to n. Okay, so this is how I'm writing. So I know that TVK will be written as some linear combination of WJ with some scalars. Okay, that scalars I'm denoting it by AJK. So to record the map T, so this exercise actually tells you that it is enough to record the TVK. So, but this once you write in terms of this basis of WJ, this TVK, then it actually says to say what is TVK. It is enough to say what are these scalars AJK. Okay, so that means, so recording this AJK amounts to recording what is T. So that is what actually defined as matrix of this T. So what is this matrix of T with respect to the basis V bar and this W bar is given by, this is the M by N matrix. So this M by N matrix is actually defined to be this AJK. Okay, so this is an m by n matrix. So if you want to visualize how it will look, okay, so this, so you are taking this W1, etc., Wm as rows, and then you are forming this m by n matrix. Sorry. So this is an m by n matrix. So you have this V1, etc., Vk. So this is or corresponding to the columns. So the kth column entries are filled by this AJKs. So this is A1K, A2K, and so on, and then AMK. So this will be the kth column. Okay, so that is how you are recording this matrix of T with respect to the basis V bar, W bar. So you can actually, if you know this matrix, then you can recover T completely. So if you want to know what is T, then you should know only this map or this matrix M of T V bar W bar. Of course, it actually uses this coordinate system. So choosing base is actually giving coordinates. Okay, so you have these coordinate systems V bar and W bar. Those also you need to know. Okay, how you are writing in terms of. So that is why, like, so assuming that this data V bar W bar is already known to you, because most of the time we will be working with some known basis. Okay, so T can be recovered from this matrix of T. Okay, so this is how one can associate. So now once we associate this matrix for the linear transformation, then we can ask like various questions. Okay, so that I will actually state it as some of the easy questions as exercise. Okay, as an example, let's see one example. Okay, so if you want to calculate the matrix of this linear transformation, let's say from this two-dimensional space to this three-dimensional space. Okay, so so what is this map that I'm giving? So I'm defining it on the standard basis, 1 0 comma 0 comma 1. So T of 1 comma 0, I just send it to 1 2 7, let's say, and then T of 0 comma 1, then I send it to just 3 5 9. So then if you take standard basis here, okay, so standard basis here will look like E1, E2, E3. So what is EI? EI is actually 1 0 0 0, ith position 1, and then 0 0. Okay, so here I'm writing everything in row form, but you can also take column form. That is not a problem. So if you take this, if you put transpose here, so this is you can think the basis vectors as column vectors. Okay, so in particularly EI will be just 0, etc., 1, etc., 0. So this EI, this 1 appears at ith place. So this is the standard basis you must have seen. So now what will be the matrix corresponding to the standard basis? So this standard basis E bar. Okay, so let me just write down E1, E2. So this is for the two-dimensional thing, comma E1 3, E2 3, E3. So I'm just putting that dimension because this is 2 coordinates and this one has 3 coordinates. So this looks like this must be 2 by 3 matrix. So it will be 1 2 7 and then 3 5 9. Okay, that is how we have defined. Okay, so this is my 2 by 3 matrix. Okay, so now we have associated matrix with a linear transformation. So now what you can do, there are some basic operations of linear transformations. Okay, so for example, if I take the space of all linear transformations, so which I denoted by home f v comma w. Okay, so I use this notation to denote the set of all linear transformations from V to W. Okay, so you know that this is actually a vector space over F. Okay, so this is actually a vector space over F. So how this addition is defined? Suppose if I take two operators T and S from this home V comma W, okay, then the addition is defined pointwise. Okay, S plus T of V is defined to be S of V plus T of V. So this is for all V in V. Okay. Similarly, the scalar multiplication is lambda T of V is defined to be lambda times T of V for all V in V. So this is a new map. Okay, this S plus T and lambda T, they are new maps, so they are defined like this. Okay, so this is the definition of addition and scalar multiplication for this home space. Okay, so then this makes this this space as a vector space. Okay, over this F. So does anyone knows whether this space is finite dimensional or not? Has anyone seen this space?
Yes.
Dimension of V into
Dimension of V
into dimension of W.
very good. So the dimension of this space is actually, okay, so here is an exercise, very well-known fact about this home space. So the dimension of home V comma W is actually equal to, so dimension of V times dimension of W. Okay, that is N and N. Okay, so now so you can actually define one very explicit linear isomorphism from this home V comma W to this set of M by N matrices. Okay, so the map, okay, let me define. So this is you can actually verify. So this exercise actually gives this earlier one. So you can define this map phi from this home V comma W F2, the set of all matrices M by N matrices over F. Okay, so how I am defining? You take T and then you just send it to this M of T comma V bar W bar. Okay, so I have told you how to associate this this matrix now. Okay, so once you fix this basis V bar and W bar for V and W, then I know how to associate this matrix M of T V bar W bar, which is nothing but AJK M by N, where TVK is defined to where AJK defined to be TVK equal to summation AJK WJ. So this is the equation you should remember. Okay, so where this TVK is defined to be summation AJK, where J is running from 1 to N. Okay, so that is how this matrix is defined. So now what I'm saying, this map that I'm defining is actually a well-defined map. Okay, so this is indeed an isomorphism of vector spaces. So this is an exercise. So phi is an isomorphism of vector spaces. So first thing is, okay, so what you can try to prove first. So first thing is this map is actually a linear map. Okay, so first of all, when you define a map, you should actually check whether it is well-defined map or not. So that is obvious. Okay, because once T is fixed, then the matrix is defined uniquely. So there is no way because V bar and W bar is fixed. So this map is well-defined. Now, suppose this matrix is actually, so to prove that given a linear transformation is actually a one-to-one map, so how one can check that whether it is a one-to-one map or not? Is there any
kernel is trivial?
Yeah, one can actually look at the kernel and then try to check whether the kernel is trivial or not. So is it true here? Kernel is trivial. So because what will be the kernel? Kernel will be those linear transformation T such that the corresponding matrix will be 0. So if the matrix is 0 means all the entries are 0. If all the entries are 0, then if you go back to this equation, okay, this equation, then what will happen? This TVK will become 0. If tvk is 0 for all k, then what will happen?
Ajk must be 0.
Yeah, then t must be 0. Yeah.
Because of that is basis, therefore you will get a scalar must be 0.
Yeah. So no, we are assuming ajk is 0, then we are proving t is 0. So if all the matrix entries are 0, that is ajk is 0, then that will imply tvk 0. Then that will imply that is true for all k, so t will be 0. So that means the map that phi that I define is actually 1-to-1 map. So this is on 1-to-1 map, and both spaces actually have same dimension. That is not hard to prove, or you can actually create. You can start with some matrix here, and then you can actually prove that there is a transformation that is actually coming from that matrix. So can you actually tell me how one can get that? If I start with the matrix here, let's say A, which is ajk, then how do I define this t here?
Tx equal to x, standard basis you can take.
No, bases are fixed. This v bar and w bar are already fixed. That is fixed for capital V and capital W. So what I'm giving is only A, which is ajk.
T of V will be A times V.
T of
V will be A times V.
Okay. So then what do you get? But what do you mean by this? How are you writing V as?
V will be written in terms of the basis.
That V1, etc. Vk?
Yeah, yeah.
Okay. So then you are using that coordinate. So that means you are writing it as column. Is that correct? So V, you want to write it like C1, etc. Ck. So that means V equal to summation Civa.
No, I mean, sir, we are looking for a particular linear transformation associated to a given matrix, right?
Yeah, that is true, but I already fixed the basis, nah? So I don't want to have like, so here, see this matrix, what we are getting with respect to these bases only. That is very, very important. So what you are saying is actually, I guess you are fixing the standard basis.
T of Vk equal to ajk summation Wij, the same thing we can take.
Yeah, so if you go back to that original formula that helped us to define the matrix, that formula we can take. There is no issue. Once you know ajk, then we know how to define tvk.
Yes.
So that means, so what you said is also correct, but you need to use this coordinate system. So you can write it as C1, etc. Ck, but you should write it like this, where V is equal to summation I range from 1 to n.
Yeah.
Okay. So then A will be m by n matrix, and this will be n by 1 matrix. So you get whatever. So, but that is again, you are writing it as other coordinates. But if you don't want to use that coordinate like this, usually we use this notation for the standard basis, nah? So better not to use. So then we can directly take this tvk equal to summation ajk wj. So we can simply take this formula. Okay, there is no issue. And then use this formula to define t. So that means maybe if you want, you can call it ta. So this a, and then I'm defining this ta. Now you can check, if I take this ta, then this a will be this matrix of this ta with respect to v bar w bar. Okay, that follows immediately from the definition. So that means this map that we have actually defined is actually isomorph, because I have given you very explicit inverse also. Okay, so that is all like already set up. So this is how it should be. So that works. That's all. So, okay, so we understood something about this home space, so which is home v comma w. So, but the thing is, we also have, we can like, because these are all like linear transformations, in particularly they are maps between vector spaces. So apart from this addition and scalar multiplication, we can do one more operation. So can anyone guess what is that?
Composition.
Composition, yeah, exactly. So because we are dealing with maps, so I will be able to do composition. But to do composition, I need to be somewhat careful, because I can't randomly do composition. So when I can do composition, suppose I give you two maps, okay? So V2W.
V and W must be same.
So somewhat like range and the domain of the second map, something should be same. So for example, like we can have situation like this. So let's say T is a map from U to V, and S is the map from V to W. So then I am allowed to do this composition ST. So which is a map from U to W. Is that correct?
Right, sir.
Yeah. So now if you take T to be linear transformation, S to be linear transformation, what will happen to the composition? That is also linear transformation. So that is easy to check. Okay. So now what I can do, I can actually fix basis. Okay. So what I can do, I can fix a basis U bar. Okay. So let me take dimension of U to be P. Okay. And then dimension of V to be N as before, dimension of W to be M. Okay, so these are all the numbers that I am looking at. So I'm looking at this ST. So then U bar I'm fixing, that is U1, etc. UP. And then V bar is already given, W bar is already given. Okay, maybe I will write V bar is V1, etc. Vn. W bar is W1, etc. Wn. So this is all given, let's say. This is all given to us. So now what I can do, I can actually take composition of maps and then look at what happens to the corresponding matrix. Okay. So this is very simple thing. This is something you must have already seen. So this is called matrix multiplication. Okay. So I'm not going to prove this because all of you know this. So I'm going to write down what is the answer. Okay. So now what I can do, so what is given, U to V, it is T is given, V to W, S is given. So I can do this composition, that is ST. So now what I can do, I can actually look at this matrix of ST with respect to this U bar and W bar. Because this basis and this basis. So usually we take the domain basis and then codomain basis. So that is I want to compute. So anyone guess what it will be?
Matrix of S times matrix of T
Yeah.
in the respective bases. Yeah.
Respective spaces. Yeah, with respect to respective basis. Okay. So that means, so what is the matrix of S? Matrix of S with respect to V bar and W bar. Okay. So because this is S, so this is S. So this is S. So similarly, matrix of T U bar V bar. Okay, so corresponding things separate. So this is somewhat very simpler thing. That is how actually we define the matrix multiplication, and all of you know how to define the matrix multiplication, and it just follows from that. For example, what will be the dimension of this space? So this is M by N, and this is actually, this matrix will be N by P. So what you get is actually N by P matrix. Okay, so that is how it's done. So maybe I will just show it in the matrix. Okay, so how you do this matrix multiplication? Suppose if I take this matrix S V bar W bar, then it will look like something like this, and then this M of T U bar V bar looks like something like this. Then if I want to calculate some ijth entry of this product, then I will look at this ith row, and then I will look at this jth column. Okay, this is the jth column. So then I take these entries, the first entry here, AI1, and then here this B1J, and multiply, add them, and then AI2, and so on, AI, so what is this, N, and then like B2J, and so on, BNJ. So then the ijth entry of this product will be summation AIR B or J, where R range from 1 to N. So this is the ijth entry of the product. Okay. So if I call it, this is capital A, this is capital B. So this is the product. So you have to show this is what you get if you are doing this composition of this maps. So okay, that is something very, very easy. Okay, that because you know how to compose, and you can just check with respect to the respective bases how they look, and then if you write down, you will get the formula. Okay, so it's very, very simple. But this is something useful, very, very useful actually. This allows us actually to do lots of understanding about this change of basis. Okay, so we will use this formula. So let me write down that formula again. Okay, I will call that formula star. So which will be very, very useful. Okay, so what you have is U2V, V2W. If you have a map T, yes, then you can do this composition ST. Then what you have matrix ST U bar W bar is same as matrix S V bar W bar times matrix T U bar V bar. Okay, this I'm calling it as star. So this is very, very important identity for me. Okay, so now what I'm going to use I'm going to use this identity and then understand what happens if I change one basis to another basis, and then how the transition matrix will look like, and then if I fix some linear transformation and then study that linear transformation in terms of one basis and another basis, then how it looks like. Okay, so how they differ and so on. So these questions can be answered using this this simple formula. Okay, so let's do that one by one. So first I will define what is this transition matrix. Okay, so which is also called a change of basis matrix. So what is that? Okay, now what we will do, we will actually only consider same space. Okay, so we will actually go from one basis to another basis. So that is called change of basis. And then you want to understand properties, some of the properties that you are interested in, how they actually changes with respect to this change of basis. Okay, so first let me write down. So what is this change of basis? Okay, so now on we will fix the vector space, so which has dimension n. So then what I can do, I can fix a basis v bar, v1, etc., vn. Okay, so this is basis of v. So now what I want to do, I want to take another basis. Okay, are all possible bases that I can actually produce for v. Okay, so if I take another basis, so let's take another basis and then study what happens to that, how actually it related to that one basis that we fixed. Okay, so take another basis, call it w bar, which is w1, etc., wn of v. So then what I can do, so because I have this basis v bar already fixed. Okay, so once you fix basis, that means you are fixing a coordinate system. Most of the time we will work with standard basis. Okay, so that is your fixed basis always. Then you take some other basis and then try to understand that new basis in terms of the standard basis. Okay, so sometimes you call this is old basis. So, and this is a new basis. Okay, so we want to understand the relationship between them. So then what is the meaning of that? Okay, so can we say anything about like how one can write new basis in terms of world basis? If you write that, of course we will be able to write. Then how that so what is used in writing that? Okay, so how can we understand that transition? That's what we are trying to ask. Okay, so because both of them are bases, of course we can always write each element wk as sum of some ajk vj where j range from 1 to n. Okay, this is I can always do for each k in between 1 and n. So now to understand this new basis wk, it is enough to understand these scalars ajk. So that means I can record those scalars, and then recording that scalars is same as recording this new basis. Okay, so this is something I already fixed. So this basis I have already fixed. For example, you can take it to be standard basis. So then what you are doing, you are taking another basis and then writing that another basis in terms of the world basis, and then you are seeing that some entries aj k's are involved. Okay, some scalars are involved, and recording that scalars somewhat helps us to get all information about this new basis wk. So this matrix I am recording as ajk. So this is called a transition matrix. So if you know this transaction matrix, you know how to go from your basis, that old basis, to this new basis. Okay, this is also called change of basis matrix. Okay, so we need to understand this, but there is some simpler way to actually put this. So if you just note this, what I can do, I can just take this linear transformation identity from V to V, then I can actually write down this A as that matrix corresponding to identity with respect to these two bases U bar, V bar. Okay, so this is nothing but A can be seen as matrix of identity with respect to U bar, V bar. Okay, so that is why I introduced that matrix of linear transformation with respect to two bases U bar, V bar. So that way you can understand all of these change of basis very well. Okay, so this is something actually we get immediately. So now one can ask, so we got a matrix which is actually helps us to go from one basis to another basis. Okay, so what can you say about this matrix? So can anyone guess what we can say?
Invertible always.
So this transition matrix is always invertible. Yeah. So this transition matrix M of I U bar V bar is always invertible. So what will be the inverse?
Mi V bar U bar.
Mi.
Sir, as per our notation, it should be WV, right? Identity matrix with respect to W bar and V bar.
No, this. I have fixed. Okay, sorry. Yeah. So I will change it to. Okay, I will change it to U here. Sorry, I mixed up some notation. Yeah, now it's fine, nah? Yeah. Okay, so let's prove this. Okay, so this is again just follows from the identity that we wrote. Okay, so recall this identity. So here is the proof. This is very simple from that matrix multiplication identity. So recall. So how we wrote. So if you have M, S, T, U bar, V bar, sorry, W bar, that is equal to M of S, V bar, W bar times M of T, U bar, V bar. So this is something we know. So now what I can do, I can take or substitute S equal to T equal to identity and W bar equal to U bar. So then what we get? So then we get on the right side, it is W bar is U bar. So this is M of ST is identity. So both are identity, U bar. And then right hand side, you get M of identity, V bar, U bar times M of T, U bar, V bar. Sorry, that is also identity. But what is this? M of I, U bar, U bar. If you take identity transformation, if you fix both bases, then if you write the matrix corresponding to this U bar, then what will be that matrix of identity with respect to U? So it should be identity. Yeah, exactly. So this is identity. So that means, so the product of these two is equal to identity. Now, similarly, you can prove the other way, okay, by interchanging the role. So that means they becomes inverse to each other. Both are invertible as well as they are invertible. They are inverse to each other. Okay. So this transition matrix is always invertible. So this transition, this change of basis matrix is very, very, very important. Okay. So now I will leave one exercise, so which is actually very, very important. So what we have seen that once you fix a basis V bar, so once you fix this basis V bar, then any other basis U bar must be actually like coming from, okay, if you want to use this notation, okay. So if you fix the basis V bar and then this another basis U bar will be given by this equation, okay, where this scalars AJK, they will form an invertible matrix. So this transition matrix is invertible. Now you can ask the converse, okay. Suppose if I start with invertible matrix P, which has entries AJK, and then take UK to be equal to summation AJK VJ. Then you can ask this question, whether this UKs will form a basis or not. So what do you think?
It will form it.
Yeah, it will form. So if you start with P, so which is a matrix, so which is invertible matrix, okay, I already used this notation, GLNF. So then I'm writing this UK as summation AJK VJ, where J range from 1 to N. So then what is my claim? This U1, etc. UN is indeed a basis of P. Okay, so this tells you that how to go from one basis to another basis if you fix a basis. Okay, so the transition matrices should be invertible. That's what it says. So this is something very, very important because that is why, like, if you go abstract, then we fix a basis and we never care about like which basis we fix. Okay, so it is good to work with some abstract basis instead of a standard basis. If you fix the standard basis, then it's like you are fixing the coordinate system. Then you have to do everything with respect to that. But most of the time, what happens if you change the coordinate system? That means if you change the basis, then confusion starts emerging. Okay, you should understand what happens if you change the basis. If you understand that very well, then most of the problems will be solved. Like most of the confusions will not occur actually.
Sir, we are assuming VA is our basis, right? We are assuming VJ.
Yeah, VA is our basis. That is given basis, let's say. Or if you want, you can take it to be standard basis, not a problem. Okay, so now what I want to actually talk about, okay. So now we talked about this transition matrix. We actually saw that it is nothing but a matrix of the identity with respect to two bases, okay. So I can of course do this for any linear transformation. So there is no like problem there is nothing specific about identity matrix. Nah? So what I can do, I can actually take linear transformation from V to V. So, and then I can fix a basis of V. Okay. So now what I can do, I can talk about the matrix of this T with respect to this basis. So what it will be? So for simplicity, we just denote it by M of T V bar. So which is defined to be the matrix T V bar V bar. Okay. So most of the time, that's what we do now. We just fix a basis and then we just work with that one particular basis. We don't usually change the basis. Okay. So in that case, if you fix a basis V bar, then you can actually talk about the matrix of T with respect to that basis. So that is nothing but you take images TVK and then write down that in terms of only that linear combination of VIs. Okay, that scalars that you get, that you collect, that will be your matrix of T with respect to V bar. So then you want to understand how this matrix actually behave. Okay, of course, this actually carries all the information about T. Now, what do you want to understand? You want to understand, okay, this is with respect to some basis that you have fixed. So what happens if you change basis? So how this matrix of T with respect to that basis changes? So that is something you want to understand. Okay, so let me state the theorem first. Okay, so it's a very, very important theorem, and then I will prove that theorem. So here is the theorem. So what it says, so you fix this linear transformation T from V to V. So I denote it by endomorphism of V. And so two bases you fix, V bar and U bar. So this is basis of V. So now I want to understand how this matrix of T with respect to U bar and matrix of T with respect to V bar linked. That is what I want to understand. Okay, so then what we can prove is actually the matrix of T with respect to U bar will be just conjugate of this matrix of T with respect to V bar. So where this conjugation again happens, not some arbitrary matrix, this is very specific matrix. This conjugation is done by this transition matrix from U bar to V bar. Okay, so this is M of I U bar V. So this is the theorem. So very, very important result. Okay, so you can actually, given a linear transformation T, you can talk about the matrix of T with respect to some fixed basis. So now what I am trying to understand, so what if you change that basis? Okay, so if you change a basis, then of course I can actually talk about the matrix with respect to the new basis. Okay, so this is the new basis. Okay, this is new basis and this is old basis. So then you want to compare them. So if you compare them, then what happens? So these two matrices are actually conjugate, and this they are not just conjugate, conjugate by this very explicit transition matrix from U bar to V bar. Okay, so this is very, very important. Like, so most of the books actually does this proof without actually, so because it's all done for one single space, so they just try to actually do this, but indeed it's a corollary of that matrix multiplication. Okay, so this proof is far better than, I would say, the proof that you find it in some of the books. Okay, for example, proof that you see in Hoffman-Kunchandal, it's not that great. So this proof I have actually taken it from this linear algebra done right. So that book. Okay, so let's prove this. Of course, the proof actually just uses that formula. Okay, so let me just recall this formula. Okay, this is the formula. So what we will do first, we take W bar to be U bar, and then S to be identity. Okay, so this is the star, remember. So what I'm going to do, I'm going to substitute W bar to U bar and S to be identity. So then what I get, let's see. So S is identity, so M of T U bar. So that's what I get on the left side, M of T U bar. On the right hand side, I get M of I V bar U bar times M of T U bar V bar. Okay, this is what I get. So this is identity I'm putting. This is U bar. This is T U bar V bar. So that stays as it is. So here I'm getting U bar. Okay. So that is the thing that I get. But this is nothing but what? This is M of T U bar, which is nothing but this. So A is I have taken to be M of I U bar V bar. So this is A inverse. So if I multiply by A on both sides, so then I get A times M of T U bar equal to M of T U bar V bar. So this is what I get. Okay, this is one equation I get by substituting this W bar equal to U bar and S equal to identity. Similarly, what you can do, okay, similarly, you can actually substitute W bar equal to V bar and T equal to identity and S equal to T. Okay, you have to interchange the role. So if you do that, okay, if you just work it out, then you will get M of T U bar V bar is equal to M of T V bar A. So this is what you get. So this is my second identity. So 1 and 2 implies the following. So what it gives if you just put them together. So because these two are equal, so this and this are equal. So it gives me A M of T U bar is equal to M of T V bar A. So this is what we wanted to prove. Okay. So if you look at this identity, this is what we wanted to prove. So that means if you take this linear transformation and then look at the matrix of T with respect to one basis, and then if you change a basis and then look at the matrix of T with respect to another basis, then the relation between them is actually given by this translation matrix and what it is. So they are conjugate under this translation matrix. Okay, and this matrix also very explicit, like I told. Okay, when you're looking for this some nice canonical form from this similarity class. Okay, so there is some translation matrix involved, that P that is involved now. So A equal to P BP inverse. The P we need to compute, and computing P is actually nothing but you are computing the translation matrix of this between these two bases. Okay, that is also given to you. So so the amount of work that you need to do that is actually much lesser, much less than directly working with this, directly doing some computation for A. Okay. Okay, so this is somewhat convincing you that, okay, so if you are looking for, so okay, so let me actually complete the story, because what we are interested in this matrix multiplication. Okay, so given matrix A from n by n matrix over the field F. So what we were interested in doing computations for A. So if we wanted to compute A square, A inverse, and so on. Okay, that is what we were interested in. Then how we actually kind of translated that problem. So we defined this new linear transformation from Fn to Fn. So what is the transformation? That is given by TA of x equal to Ax. So that is what we define. And then most of the time we fix the standard basis. So that I call it E bar, which is E1, etc. En. So then this is the standard basis of Fn. So then what happens? So this is some simple exercise for you. So if you look at this matrix of this TA with respect to this standard basis, okay, so then that will be just A. So it is not that hard to, okay. So now if you change the basis, then there will be this transition matrix, okay. So then what happens if we change the basis? Then what happens? The matrices correspond to that new basis, okay, that M T A with respect to this new basis. So this will be conjugate to this capital A. Okay, that is what we proved. So you can ask this converse question. Okay, suppose if I start with some invertible matrix from invertible n by n matrix, so then I can actually, like I said, I can define this V bar to be V1 etc. Vn, okay, where Vk is given by this P Ek, okay, which is very explicitly summation, let's say P equal to Pij. So then this is given by P or J E R, where, sorry, P or K, because I have fixed K here. K range from 1 to. So I'm actually, what I'm doing, like, once you fix this standard basis, if you take the invertible matrix, you know how to get this new basis, okay, with respect to that invertible matrix. So that is what we saw now. So getting a new basis is same as taking this invertible matrix and then like applying that invertible matrix on this basis vectors. Okay, that is what we saw. So if you take that new basis, call it V bar, then what happens? Then you can talk about this matrix of that linear transformation TA with respect to this V bar. Then what will be that? So the transaction matrix will be P. So it will be actually PAP inverse. So you can actually directly compute and then see. I guess, oh sorry, not PAP inverse. It will be P inverse AP. Okay. So this means, so given matrix, so you can see that given matrix, you have a linear transformation, and that linear transformation with respect to standard basis gives you that matrix back. And if you take any other basis, then you can actually see that the matrix of that linear transformation with respect to that basis will be the conjugate of this A. And any conjugate also can be made into like a matrix of this TA, okay, with respect to that some basis. So that means, so this is completely kind of characterizes all the similarity classes elements. Okay, so basically what you need to study, okay, so if you are interested in doing any computation about A, then what you need to do, so we are looking for possible like simplest conjugate element. Okay, so look at that similarity class and then look for some very simpler form element in that similarity class. Okay, so if you're interested in doing that, then what you can do, you can simply look at this linear transformation TA, which is given by TA of x equal to AX, and then find some suitable basis of this n-dimensional space such that with respect to that basis, you write this TA, matrix of TA. Okay, then you know that that matrix of TA with respect to that suitable basis will be conjugate to this A. And if that matrix looks somewhat simpler, then that is the simplest form that you are looking for in that similarity class. Okay, so that is why, okay, the problem of finding some simpler form inside the similarity class turns out to be finding, okay, so the problem actually becomes finding some nice basis of your space, okay, it could be Fn, such that the matrix of this TA with respect to that basis looks simpler. So I still haven't told you what is simpler and so on. Okay, and we will discuss this, discuss that in next class. Okay, so what is the meaning of simpler and so on. For example, I can actually tell you like, so if we can make it diagonal matrix, that is well and good, but that cannot be done always. Okay, what is the best you can do? You can try to make it a block diagonal. Okay, what will be the block diagonal? Block diagonal looks like something like this. Okay. So then A1, A2, A3, and so on, some AK will be there, and all other integers are 0. So this is called block diagonal matrix. So why are we looking for something like this? So that also will become very, very clear. Okay, so like, for example, like, what will be the determinant of this block diagonal matrix? Can anyone tell?
Product of determinant.
Yeah, so it will be just product of A, determinant of A. And what will be the inverse of this block diagonal matrix?
Each A inverse, that one.
Yeah, it will be like, take the corresponding block inverses. That will be again squares, cube, everything will satisfy the same property. Okay, somewhat like the problem. So your n is really, really large. Okay, and then suppose if we can decompose into like some 10 by 10 or 8 by 8 matrices, somewhat smaller block matrices, then that is also well and good, because you can't deal with 1000, but you can deal with 8, 10. Okay, so somewhat your computation cost will become very, very much less. Okay, so that is what actually we will be actually trying to do. Okay, so this is our problem. So we want to find some nice basis of the vector space that we are working with, so that the linear transformation with respect to that basis, the matrix of the linear transformation with respect to that basis, looks much simpler. Why we want to do that? Because if you go from one basis to another basis, the corresponding matrices will be conjugate. So that means finding some new basis with respect to that, the matrix looks simpler, is same as finding some suitable canonical form from that similarity class. Okay, so that is why we are actually looking for some suitable basis, so that the matrix of that linear transformation with respect to that suitable basis becomes much simpler. Okay, so I will tell you like in next class how to do. And yeah, there are like, of course, many ways to do this, depending upon whether your field has enough roots or not. And yeah, let's see how much we can do in 2 classes. Okay, I will stop here because I'm running out of time.
Thank you, Venkatesh. So I think we will take a 8 minutes break. We will meet at 7:10 again.
Is there any question? Okay, so yeah, I'm trying to write some notes for this. So maybe I will share it with organizer later.
Okay, that will be nice. Yeah.
Okay. Yeah. Okay, then, thanks. I will stop sharing.
Venkatesh, can you send me this PDF file of this notes?
Yeah, sure. Yeah, I will.
Okay.
I still haven't written notes for the first talk.
No, the one just which you are like the running notes, the one which you are just writing.
This one I have already properly written. I will share that. No
Okay.
problem.
Yeah. Okay. Thank you.
Okay. I will send it to you.
Yeah, and tomorrow I think we have a tutorial for them at 6 p.m.
Okay. I actually have written some problems as part of the notes.
Okay.
Maybe those problems can be discussed. And
Yeah.
again, like some other problems also, I will formulate and then send it today.
Okay, sure. Thank you. Then they will have some time to look into it.
Yeah, definitely.
Okay. Okay.
Sir, which app do you use for the writing purpose? Venkatesh sir?
I am using Microsoft. Actually, this is Lenovo laptop. So this has Windows. It's called Journal.
Journal.
Yeah.
Okay, sir. Okay, sir.
So Linux actually has the journal version. It's called external something. Instead of J, you put X. That is free actually. This is free if you have Windows. It works only in Windows and.
Okay, sir. Okay. Thank you, sir.
Hi. Good evening, Divakaran.
Hi.
Hi. So we'll just start in 2-3 minutes.
Yeah, certainly.
Okay. I think we can start now.
Okay. Okay. So, good evening, everyone. Nice to see you all again. I hope, like after yesterday's session, you all could go back and think a little bit more about whatever we discussed. I would first like to ask, is there something that you would like to tell me or you would like to discuss with others from whatever we saw last day? If yes, we can start from there, else I have something planned for you. So.
I was thinking of something that usually when we imagine of an unbounded function or we try to visualize it, usually we think of something like 1 by x, right? We say that something which blows up at a point. This is the usual term, I mean, we very casually use. But we never think of something like 1 by x sine 1 by x. Like it doesn't blow up, but it gradually becomes bigger and bigger and bigger, right? So I think in class, when we give an example of unbounded function, I think we could also talk of this 1 by x sine 1 by x.
Yes. So I think something similar we talk about in like, so for example, maybe those who have seen complex analysis, it would make a lot more sense to you. So 1 by x is like a pole, but 1 by x sine 1 by x is like an essential singularity. Does that make sense to you, to people? Like, that's how I would think about it, right? So when we study complex analysis, there are two kinds of functions. There are, of course, the easiest is holomorphic functions, like complex differentiable functions. Then the second category of functions are like meromorphic functions, like functions that are not differentiable, but in the power series, you have like a few like negative powers of x also, like 1 by x power n, or like some such factor will be there, but that's it. So then we say that it has a pole, the function has a pole. But these are still somewhat special. These functions like that, those are meromorphic, are also somewhat special. And then the worst are things which have an essential singularity. So actually, you can take any function with an essential singularity and just replace it by the real version of it. You will get something ugly like this. So that's one way to produce such ugly functions, if you would like. So did that kind of make sense, Shobhan?
Yes, that makes sense. Yeah.
That's how I would think about it. So a lot of these things makes more sense when we study complex analysis. Like that's how things are. I don't know why, but that's how things are.
That's true. Yeah.
Something interesting is, so usually when I talk about as in mixing functions, to get an idea of what graphs of function look like, and how do you manipulate the graphs of functions. One of the functions I usually pick is sine 1 by x, sine x by x, and all these combinations. But somehow yesterday is the first time that I thought about 1 by x, sine 1 by x. Every other combinations I have made, I'll be like, plot this, see what happens. But except this, somehow yesterday is the first time that I came across.
Okay, nice.
Professor Divakaran, I think so. What I got to know that I think you were saying that any function having essential singularity can approximate any value in C. Am I right?
Yes. If it's an essential singularity, then in any neighborhood, all values are taken. So something like that. So yes. So here also, like something similar is happening, right? I'm using a loose analogy. Like here also in near zero, all values between -1 and 1 are being attained. Like something like an essential.
Something like that.
Cool. So that's what I was trying to say here.
Thank you.
Okay, so if there's nothing else, let's start. Please enable sharing. I think I'm not enabled, like I'm not allowed to share as of now. Sushovan? Share screen is not enabled.
Yeah, just try now. Yeah.
Okay, now I should be fine.
Yeah, Divakaran, I have the one question.
Yeah.
For the IVP, we can discuss the continuity, discontinuity, or jump, different type of things. But for the continuity, this is required to discuss the IVP. Without IVP, we can't discuss the continuity. Generally, we have not seen anywhere, and nobody is talking or indulging the IVP when we talk the continuity.
That is not true, right? Because the IVP is used in so many proofs, including like Rolle's theorem and hence mean value theorem and all that. So, in fact, most of the important theorems have IVP hidden inside.
But when you go along after learning the continuity, then we use the continuity. That is a different thing. But to understand that continuity, IVP, why we involving, or any other thing, why we involve?
Okay, that is because, as I said, like that, I brought up IVP because it's something intuitively makes sense, right? One of the two definitions that one of you gave was directly related with IVP. So the D1, if you remember from yesterday, D1 was almost like IVP. And that is why we started talking about IVP. That's why we brought up. In fact, intuitively, for the definition of continuity should be based on IVP. That was the intuition we had. So that's why we should bring up IVP into the discussion of continuity. So that is your question.
So when you talk, or when we have to talk the teaching pedagogy, we have to, when you talk the continuity, do you have to discuss the IVP, or because IVP come later? Because generally we have to tell the what is IVP, then we discuss with the continuity.
So I'm not saying you have to do it this way. Okay, it's all up to, like, see, different people have different styles of discussing topics. So it's not like you have to discuss IVP and then go to continuity. That's not true. That's certainly not true. But this is one way of looking at the subject. Okay, this is one way of looking at the subject. There are other really good ways of looking at the subject. I'm just like sharing this is very much my own thoughts, my own biases will automatically come in when I'm talking about these things. So I think each person, each individual, each of us would be looking at the subject in their own, using their own eyes, right? Their own perspective. So it's part of that perspective thing. So there is no like, okay, you have to do it this way. I think there is some merit in showing it this way because intuitively the word continuous is naturally related to IVP, because continuous is the opposite of having breaks. Having breaks is, and that is really, IVP is exactly capturing that. Not having breaks is exactly what IVP is capturing. So I feel it makes a lot of sense intuitively and historically to talk about IVP, but it's not necessary that one has to start this way. This is absolutely not necessary.
Can you sum up what you taught finally, one or two line, continuity and IVP? How this?
Yes. Let's recall what we saw last time, right? So last time we saw, we discussed what IVP is, we discussed what continuity is in some sense, and then we saw that IVP does not imply continuity, and continuity does not imply IVP. These are the two things that we saw. IVP does not imply continuity. The example was our sine 1 by x function. Of course, not just sine 1 by x, it's the more complicated function, f of x equal to sine 1 by x, if x is not equal to 0, and 0 if x is equal to 0. So this function illustrated that IVP does not imply continuity. And the other function that showed that continuity does not imply IVP was this example. So you look at the function f from 0, 1 union to 3 to r, defined as f of x is equal to 5. This function showed that continuity does not imply IVP. So these were the two things that we really understood throughout yesterday's 1 hour, that's really what the only thing we discussed. We understood what IVP is. We understood what continuity is. We saw that IVP does not imply continuity. Continuity does not imply IVP. That is really the crux of what we saw yesterday. So in short, this is the summary of what we saw yesterday. Did that help?
Yeah. Thank you.
Great. So now let's come back to what one of you actually had mentioned yesterday towards the end. I think it was Shubhajit or somebody, I forgot. Like you had mentioned that one of you had mentioned that actually it doesn't make so much sense to talk about IVP if the domain is not connected. So here, for instance, the issue was partly that the domain is not connected. It has two pieces, right? 0, 1 union 2, 3 is a disconnected set. And actually it doesn't make sense to so much sense to talk about IVP when the domain is disconnected. Okay, so now we are going to restrict our attention. We are going to restrict our attention to connected domains, because I'm going to take that opposition to whatever I was telling, and I'm going to start from there. So from now, I am going to only talk about connected domains. So what are examples of connected domains? The only connected domains in R are intervals, basically. It can be an open interval, it can be a closed interval, it can be like one side open and the other side closed, and so on. But it should be an interval to be connected. It need not be open, it need not be closed, but it has to be an interval to be a connected set. Similarly, it need not be bounded. The set of all x greater than 2, set of all real numbers greater than 2 is a connected domain. But basically, it is one of these things. It's an interval. It's of the form of an interval, and those are the only connected domains. Now, suppose, like, for example, now there's a related notion. So let me try to, again, this is based on intuition. I'm going to say something. So for example, one of the other ways in which people talk about continuity is the ability to draw, like not having breaks, is also related to this idea. Sorry?
I think that was someone by mistake would have unmuted.
Okay, that's fine. So like not having breaks is also related to this other point. Okay, so we say a function is continuous if I can draw the graph of this in a continuous fashion. That means I can draw the graph without lifting the pen from my paper. So some people have used this definition historically, and we all intuitively use that. Like, for example, if I have to draw something like this, I have to lift my pen and then draw it again. So this is another way of looking at continuity. And it's related to our IVP definition, the definition that there are no breaks. If there is a break, you will have to lift the pen. That's sure, right? So not having breaks and being able to draw the graph without lifting the pen are somehow related to each other. Now notice something. Suppose I have such a graph. Okay, such a graph. If suppose I was starting from here, then I can keep drawing this without lifting my hand. So is this function in some sense continuous? Like we have this question, right? So of course, this whole point is that the reason is that we can never really completely draw the graph of such a function. If suppose the domain is the entire real line, then we cannot really expect to draw the complete graph. So maybe it's actually, again, if you are using this kind of definition, maybe it's a good idea to restrict our attention to something which is like you can finish drawing. Okay, so in what cases can you finish drawing? You can finish drawing precisely when it's not just connected, it's also closed and bounded. Suppose, for example, let's look at, like, suppose the domain itself is the entire real line, then clearly even for a function as simple as f of x equal to x, I cannot completely draw the graph of this function, right? In no finite time, I will be able to draw this graph. Without lifting my pen, or with lifting my pen, I will not be able to draw the graph of this function. Correct? On the other hand, like for example, even in, like, say, an open interval, suppose we look at this function, even this function, the issue is that I can never, like, if suppose I'm looking at without lifting the hand or something, the drawing of the graph doesn't end in any finite time. So in some sense, if suppose this is the intuition that people have, like, are you able to draw the graph of this function without lifting the pen? Then perhaps at no finite time, you are forced to lift the pen, actually. Even if you are taken the more general function, suppose you are taking the more general function of f of x is equal to 1 by x if x is not equal to 0, and 0 if x is equal to 0. At no finite, after no finite point, am I forced to lift my pen? Right? I can keep drawing this till the end of time and I would still not have to lift my pen. Only once I reach, like after infinite time, I have to lift my pen and keep it here. And then again, I can still keep drawing for infinite amount of time. So in some sense, if suppose you are using this second or like another way of looking at no breaks, it makes sense to not just restrict our attention to connected domains, but it also makes sense to restrict our attention to closed and bounded intervals. Okay, so that's what I'm trying to say. Intuitively, I'm saying that when you're talking about connectivity, maybe it makes sense to talk about connectivity only on closed and bounded sets. So from now, we are going to talk about continuity in this restricted sense. We will be talking about continuity only on closed and bounded sets. Okay, so there's a starting point, there's an ending point, and then you are only looking at points between this A and B. So that's what we are going to do. Suppose we restrict our attention to this closed and bounded intervals, then what can we say about the relationship between IVP and continuity? Now, does IVP imply continuity? Does continuity imply IVP?
Continuity implies IVP.
Okay. In this restricted case, we know that continuity implies IVP. Does IVP imply continuity?
No.
IVP does not imply continuity. Can you give me an example to illustrate that IVP does not imply continuity?
That same sign 1 by x over minus 1 to 1.
Absolutely. So you can consider the same function over the closed interval minus 1 to 1, and it does not, it satisfies IVP, but it does not satisfy continuity. So this is something, so if we restrict our attention to this closed and bounded interval, then we know that one-way implication is correct. Continuity implies IVP, but IVP does not imply continuity. So now it is natural to ask, okay, so there are two questions that we are supposed to ask. Okay, how do I know this? That's one question, question number one. Second thing is, okay, continuous functions are satisfy intermediate value property, but intermediate value, there are more functions that satisfy intermediate value property. Can we characterize all functions that satisfy intermediate value property? Is that doable? This is question number two. Let me repeat the two questions. How do we know this? That's question number one. Second question is, can we characterize all functions that satisfy IVP? These are the two questions that we are interested in. Okay, so perhaps many of you know why this theorem is true. Am I right in assuming that most of you might know why this theorem is true?
Yes.
And in fact, I was actually not planning to really talk about the proof initially because I thought most of you know, but now I have a reason to talk about its proof. Why am I? So you will understand why I am going to talk about this proof, because I feel that there is, when you're teaching this, okay, I know all of you know the proof, but I believe that I have found a technique which really helps us when we are teaching this proof. So this, I believe, at least some of you will not know, and therefore I want to discuss this teaching technique. It's a pedagogical tool that helps us when we are teaching the proof that continuity implies IVP. Okay, so that is the reason why I want to discuss this proof. So let's try to discuss the proof. Let's try to look at the proof. First, let me write the theorem precisely. So what is the theorem? Can somebody help me write the theorem? Okay, let me write it myself.
And mu is any real number between FA and FB?
Stronger than that. Actually, we can say something much stronger. Okay. Okay, you want to write it. It's actually a little stronger.
Okay, yeah. So then for every x1, x2 from AB,
yeah. So
with x1 smaller than x2.
A is less than x1 is less than x2 is less than B.
And mu is any number between fx1 and fx2.
Very good. Mu is a number between fx1 and fx2.
There will exist some point xi between x1 and x2.
There exists a point xi. Okay, I'm going to write nu because I don't know how to write psi. I'm very bad at it. So nu between
x1 and x2.
So there exists a point nu between x1 and x2 such that f of
mu is equal to mu.
Okay, so this is really the intermediate value property, right? Given any 2 points between A and B, and the number between f of x1 and f of x2, you can find a point between x1 and x2 such that f of nu is equal to mu. This is the statement of intermediate value theorem. So let's try to see what is the proof. Okay, most of you might have seen this proof already, but what I'm going to do is I'm going to give a name for the technique used in this proof. And often when you have a name, it is easy to remember later. And the name I'm going to use is real induction. Okay, we will come to why I am calling it real induction and so on later, but I'm going to call this technique real induction. And in fact, I claim that the exact same technique is used in so many different proofs that you will see in analysis. So there will be at least 10-15 theorems that you prove every year, which uses the exact same technique. And if suppose you tell students that, okay, this theorem uses real induction for proof, and you can say that, okay, these theorems use real induction for proof, then they will automatically remember all those proofs. So that is what I really want to bring in, this technique of naming something so that it becomes easier to understand it. So that is really my crux of whatever I want to discuss today. It's about naming. So I will discuss why this is a good naming also later, why this is called real induction. So let's try to see, okay, let's recall what is induction, right? Mathematical induction. What is mathematical induction? Mathematical induction says that if suppose P1 is true, that means there are statements for every n, suppose, and let's call it P of 1, P of 2, etc. In general, P of n. If P of 1 is true, and if P of n is true implies P of n plus 1 is true, then P of n is true for all n. All natural numbers, this statement is true. Okay, so in other words, how do you intuitively see this? If suppose intuitively, this is the way I look at induction. Suppose that we have a train of dominoes. If the first domino falls, okay, and whenever one domino falls, the next domino also falls, then all dominoes have to fall. This idea is called induction. And many of you would know that this idea is equivalent, the idea of induction is equivalent to something called well-ordering principle. In fact, even though I'm going to call it induction, actually it is more like a well-ordering principle kind of thing for real numbers. That's what. But still, when we use proofs, we don't say, okay, use well-ordering principle. We actually say use induction. So that's why I'm going to call it induction. So how are the two related? How are induction and well-ordering principle related? That's what I want to now discuss. So what is well-ordering principle? Can somebody say that?
Any non-empty subset of n has a least element.
Very good. Any non-empty subset of the set of natural numbers have a least element. So suppose, like for example, suppose I want to say that under this situation, all dominoes has to fall. So suppose, like, let's try to prove this. Assuming it's not true, okay, assuming that all dominoes don't fall, there will be some domino that is still standing, right? Now look at the smallest number such that the domino at that position is not falling. There will be some smallest value for that by well ordering principle. So there is a smallest value for which the domino at that position is not falling. So notice that so suppose the smallest value is n. So the nth domino does not fall. If the nth domino does not fall, then we know, and we know that it's the smallest value for which a domino does not fall, then we know that the n-1th domino has to fall, right? So but if n-1th domino falls, then n+1th domino also falls is part of our hypothesis, or that's what we have shown. If one domino falls, the next domino also falls. So it contradicts our assumption that the nth domino does not fall. Or there exists or in other words, it contradicts our assumption that there exists some domino that does not fall. So what are we doing here? Here, in some sense, what we are doing is we are assuming something, find the smallest possible number for which this is satisfied, and then say that, okay, this cannot be the smallest thing that satisfies, like that leads to some contradiction. And that is exactly what we are going to do in this proof. We will define a property and say that, okay, this property is satisfied for, say, this class of numbers. Now you look at the smallest or the biggest or whatever number for which this property is satisfied, and then show that, okay, actually this is not the smallest or the biggest. Slightly bigger number also satisfies the same property. So in that sense, this is exactly like induction. And that's exactly the kind of the proof that we are going to do. Is the intuition clear? Of course, we will go through the proof very clearly and rigorously. And maybe after that is better when we are. So try to, whenever I'm saying something, try to relate it with induction. Okay. So that's what you need to do when I'm talking about all these things. Try to relate it with induction. And then I think it will make a lot of sense for you. So let's try to do this. So I'm going to define a set. Okay.
Sorry, sir. Can you please back to the slide where you have given the example of function is continuous but not IVP?
Function is continuous. Sine 1 by x.
Yeah, this one, f0, 1, 2, 3.
Oh, okay. This one. Yeah.
So if we just follow the definition of IVP that just you have written in the last slide, this example works or not? I think this will not work.
Sorry, this I said wrong. I should have written x. My bad. Yeah, thanks for pointing it out. This satisfies, this does not satisfy. Thanks a lot. This does not satisfy IVP. I wrote it wrong. Of course, if it's a constant function, then it certainly satisfies IVP. Yeah, my bad. Really, thanks for pointing it out.
No, sure, sir. Thank you.
Yeah. Okay, so let's try to go through the proof properly. So I'm going to define a set first. What is the set that I'm going to define? I'm going to look at the set. Oh, sorry, color changed automatically. I'm going to look at the set of all x in the interval x1, x2, such that f of x is less than, before that I have to do one thing. Okay, I've already done that. Okay, I've already assumed that f of x1 is less than f of x2. This is not always true. Sometimes f of x1 can be greater than f of x2 also, but the proof will be similar. So that is why this assumption is fine. So if you take a value between f of x1 and f of x2, then something happens. That is the actual statement. But here we are assuming that f of x1 is less than f of x2. Okay, so there are two options. It can also happen that mu is between f of x2 and f of x1, right? So f of x2 is less than mu is less than f of x1. That is another possibility. That depends on whether f of x1 is greater or f of x2 is greater. Depending on that, this situation will change. But for convenience, we are assuming this. The other thing also you can easily prove. Okay, the same technique will work for the other proof also. So given, suppose we take two numbers x1 and x2, there are two possibilities. Either f of x1 is less than f of x2, or f of x1 is greater than f of x2. There are two possibilities. Without loss of generality, we can assume that f of x1 is less than f of x2. And that is the only case where we are proving it. The other case also can similarly be proved, but I am not going to indulge in that. The proof is exactly identical. I hope that does not lead to any confusion. Okay, so I'm going to assume that f of x1. So I'm going to write that here. I'm going to write. So I'm going to rub this. And instead, I'm going to write here, assume without loss of generality that f of x1 is less than f of x2. I'm going to assume this. And then I'm going to say that if mu is a value between f of x1 and x2, f of x2, then so and so happens. Now, given this, I'm going to define my set. How am I going to define my set? My set is, you look at the set of all elements in the interval x1, x2, such that f of x is less than mu.
Sir,
Okay.
then we can assume that f is non-constant continuous function because constant it is obvious, right?
Correct. Again, in fact, I'm showing that it's not, I'm assuming something stronger than it is not constant. If it's constant, then f of x1 cannot be strictly less than f of x2.
Indirectly it's saying.
So I am already assuming that it's not a constant function. Constant functions, it's obvious. There's not much to do. So I'm indirectly assuming the fact that f is not a constant function here. Right? And I'm going to look at this set. I'm going to look at the set S. Now, what do? Notice that this S is a non-empty set. Why is this set non-empty?
x1 belongs to S.
As x1 belongs to S. Very good. So this, as x1 belongs to S, S is a non-empty set. Is this set bounded?
Yes, because our domain is bounded.
Yeah, exactly. It's bounded or because it's bounded by x1 and x2. So S is also a bounded set. In particular, it is bounded above by x2. Okay, so it's bounded above by x2. That's what we know. So now notice this. This is a set. This is a set that is. So again, let's go back to induction. Related with the induction, what are we doing here? We are finding a set. We are finding a non-empty set. Okay, we are finding a non-empty set, and we are doing something similar to well ordering principle. That's the whole idea. So keep relating with that. Right. So we have, first of all, we have defined a set, and then we have shown that that set is non-empty and is bounded. Now, once we have shown that, we know that if suppose it's bounded above and non-empty, then we know that it has a least upper bound. This is called the least upper bound property for the set of real numbers. Any non-empty subset of real line that is bounded above has a least upper bound. Okay, so let's call this least upper bound to be C. So C is the least upper bound of S. Let C be the least upper bound of S. Can you see that? Is it clear that there exists a least upper bound? I'm just going to give it a name, namely the least namely C. So now, in some sense, what is this? How should you think about it? So, for example, when I am relating it with induction, let me try to relate it with induction. What is this C? The C is equivalent to the first. So, for example, I said that in the induction step, what did I say? So there is a largest value. So there is a largest value such that all the largest n such that all dominoes till that value falls. Right? We did slightly differently. We actually said that there's a smallest value for n for which the domino does not fall. That means if k is less than n minus 1, then all dominoes at the kth position then the domino at the kth position has to fall. Right? What did we see? The n is the smallest number such that the domino at that position does not fall. So if k is less than or equal to n minus 1, then the domino at kth position cannot fall. In other words, n minus 1 is the largest number such that no domino before n minus 1, no domino before that does not fall. This LUB should be thought of similar to that n minus 1. So our C is like our n minus 1. Now we will use induction to prove that, okay, because n minus 1 is falling, n also has to fall. Slightly greater value will also fall. Of course, here there is no next element, there is no n plus 1, but we can show that a slightly greater value also has the same property. In other words, there is a slightly greater value, there is a value slightly greater than C, such that f of that value is also less than. And that's what we are going to prove. Okay, if suppose suppose f of C is strictly less than mu. If f of C is strictly less than mu, then this will happen. That's what we are going to prove. So, and that is why this is similar to induction. Okay, so of course there are two cases. Case 1 is f of C is equal to mu. If f of C is equal to mu, then our job is done, right? Because mu is equal to C. So this case is easy, really easy. This case is really, really easy because if f of C is equal to mu, then take C, then our proof is complete because mu is equal to C. Hence proof complete. So the really important case is only when case 2. That means f of C is strictly less than. And I said what we are going, in this case, we are going to prove that there exists a slightly greater value. Okay, there is a slightly greater value than C such that f of that value is also less than. But this contradicts our assumption that C is the least upper bound. Just like how we did in induction. So that's the trick that we are going to now do. Okay, so let's try to see how do we prove that. How do we prove that there exists a slightly greater value such that f of that value is there is a slightly, so what we are going to prove, let me just write that in red here, there exists a D strictly greater than C such that f of D is also less than mu. This is what we are going to prove. Now, and this contradicts the assumption that C is the LUB of S. That's what we want to prove. I have not proved it, but this is what I want to prove. Okay, so let's just keep this in mind because we will be proceeding according to that.
Sir, I think FC can never be mu because C is coming from a compact set x1 to x2 closed and bounded interval. So C is the supremum of the compact set, so C has to belong to the set. So C belongs to S, and that means f of C has to be strictly smaller than mu itself.
What is the compact set you are saying? Sorry.
The x1, x2.
X1, x2 is a compact set. Okay. In fact, this can happen, by the way. Okay. Let's try to see. So you are saying that C can never be mu, right? I will show that that's not the case. Okay. Let's try to understand that. Suppose let us take the function f of x to be equal to x. Simple function, right? Let's take a simple function f of x equal to x. Now let's try to see, suppose our, and I'm going to take in the interval 1, 2. So f is a function from 0, 1 to r, and f of x is equal to x. So now what am I going to do? I am going to take, let my x1 and x2 be also equal to 0 and 1 for simplicity. My x1 and x2 is also going to be 0 and 1 for simplicity.
Yeah, I got it. Yeah.
Suppose I take let's anyway discuss this because others might not have understood the point. So let's go through it. So suppose, like, for example, I take a value between f of 0 and f of 1. Let's say half. Half is a value between f of 0 and f of 1. If we take half, which is a value between f of 0 and f of 1, what is S in this case? S is the set of all...
open 1 by 2.
Yeah, exactly. So it's the set of all x in 0, 1 such that x is less than half, which is equal to closed 0, open half. What is the supremum of this?
1 by 2.
Supremum of S is equal to 1 by 2, and that is our C. What is f of C? Half, as we wanted. So it is not true that this can never happen. This can happen. This can happen, and in fact, this will happen. This, on the other hand, cannot happen, is what we are going to prove. So if this cannot happen, then this has to happen all the time, right? So it's not just that this can happen. We are saying something stronger. We are saying that this will always happen. So it's a very, very strong statement. It's not just that this can happen. It will happen. You understand the difference between can and will, right? It's not just some possibility. It will surely happen. This will surely happen because this cannot happen. That's the idea. Anyway, it's good that you asked that, because then now it's very clear, right? So this will always happen because this cannot happen. And this cannot happen uses a kind of proof like that is very analogous to induction. That's the idea that I'm going to explain, right? So what are we doing? We are saying that there exists a slightly bigger value for which the same is true. That's what we are going to show, right? How do we show that? We use continuity for that. More precisely, what are we going to do? We are going to take a suitable epsilon. What is the suitable epsilon? Okay, let's try to understand that also. Let's try to see what is a suitable epsilon. So for example, this is C, let us say. This is mu, let us say, and this is f of C, let's say. So the epsilon should lie like this. In other words, whatever the epsilon is, f of C plus epsilon should be less than mu. You have to choose an epsilon such that f of C plus epsilon is less than mu. You have to choose an epsilon of this type. In other words, what should we do? Right? That's exactly what we want. F of C plus epsilon should be less than mu. In other words, epsilon should be strictly less than mu minus f of C. So we will epsilon, any value less than mu minus f of C should work. So you have to fix some epsilon such that epsilon is less than mu minus f of C. So fix one such epsilon. If you want to be precise, for example, one such example is mu minus f of C divided by 2. That's one example, but it's not necessary that you take this. In fact, many times in textbooks, they always use this particular value, but that's not necessary. Any value strictly less than mu minus f of C would work. And the reason is precisely this. This picture is why we have to take an epsilon that satisfies this condition. Okay, so we take such an epsilon. As soon as we take such an epsilon, what does continuity say? Continuity says that there exists some delta greater than 0 such that if mod of x minus c is less than delta, then mod of f of x minus f of c is less than epsilon. In other words, f of x minus f of c is less than epsilon and greater than minus epsilon. Sorry, I'm very careless when I write, so please be wary of whatever I write. In other words, f of x lies between f of c plus epsilon and f of c minus epsilon. But we know that f of c plus epsilon is less than. That's how we chose this epsilon. So f of x will still be less than mu if mod of x minus c is less than delta. Okay, there exists some such delta. So let's try to fix such a delta. I'm going to now define nu, okay, because that was very important. So nu is a point which is defined to be x plus delta by 2. We have fixed this delta. Notice that there is this delta. I'm using that delta to define nu. Okay, so not define d nu, I use it to define d. Okay, I had called it d earlier. This d is what I'm talking about. This d is what I'm trying to define. So how am I defining d? I'm defining d to be equal to x plus delta by 2. Notice that this is strictly what x? This is, sorry, I'm really sorry. So d is equal to c plus delta by 2, which is strictly greater than c. But on the other hand, notice that d minus c is less than delta. In fact, d minus c is equal to delta by 2. Let's write it more precisely. It's equal to delta by 2, which is less than delta because delta is greater than 0. So mod of d minus c is less than delta, which implies that mod of f of d is less than mu. That was this whole thing, right? This whole thing said that. So this implies that f of d is less than mu. So we have constructed a d as we already wanted. See, this is the kind of d that we wanted to find, and we have succeeded in finding a d like that. We have found a d that is strictly bigger than c, such that f of d is also less than mu. And this contradicts the assumption that c is the least upper bound. Okay. So in other words, this cannot be the largest value for which the domino does not fall, such that no previous domino falls. There is a larger value. And that contradicts our earlier assumption that this is the largest. So it's very much like induction. And that is why it's called real induction. And please go and look at it. Look at your analysis text. How many of the theorems use this technique? The exact same technique. You define a set, and then you do exactly this. Of course, there is an ingenuity. There is some ingenuity in defining this set, however. Okay, that requires some ingenuity. But once the set is defined, everything else is just like this. It's very, very simple. So for instance, if suppose you have introduced this term real induction, then you can give many of these proofs as exercises. All you have to do is give a hint, define S to be this, and use real induction. Because the only ingenuity is in defining the set. Once you define the set and you know that you have to use real induction, everything else is automatic. And this is not just useful when you are giving exercises. It is also useful when you are remembering. Now you don't have to remember the entire proof. All you have to remember is what is the set that I am going to use. And sometimes, like in this proof, the set is also not difficult to remember. It's easy to remember. So, or easy to even come up with yourself. In this particular case, it's actually easy to come up with. There are some cases where it's not at all easy to come up with, but in this particular case, it's actually easy to come up with. And this, I believe, so this, if people understand this, they will be able to understand, understand the, like, a big chunk of real analysis in a much better way. So of course, I learned it from Stack Exchange. I learned this idea of calling it real induction, that it can be called real induction from a Stack Exchange post. I believe that at least some of you are aware of this website called Stack Exchange, right?
Yes, sir.
Math Stack Exchange. So it's a very, very good site, Math Stack Exchange, math.stackexchange.
There are other stack exchanges also related.
Yes, there are other
so many subjects. Yes,
exactly.
About like LaTeX and
yes,
other.
Absolutely. There is LaTeX Stack Exchange.
Yes.
There are so many stack exchanges. There is Stack Exchange for almost every subject now. And in fact, not just subjects. There are even stack exchanges for Those things which are not
Grammar, even like those
Yeah.
things also.
all those things.
There is a stack exchange for even wood carving.
What carving?
Wood carving.
Wood carving. Oh, I did
Oh,
not.
great.
Sir, I have a question.
Mhm.
Can you please specify one particular result
Mhm.
that says that FC cannot be greater than mu?
F of C cannot be greater than mu is also okay. So yeah, that's
Yeah, we need to consider that case as well to complete the proof, no?
yes.
Or am I missing something trivial?
You are absolutely correct. Theoretically, we have to prove that also, but that is
Yes. Actually, I was thinking of any trivial result which could eventually imply that FC is not greater than mu very trivially, but I could not find one. Yes.
Very good, very good. So that's a good point. Theoretically, there are three possibilities. This is called trichotomy. Two numbers can either be equal, or one is less than the other, or the other is less than the first one. Right? So given two numbers, f of c and mu, there are three possibilities. F of c is equal to mu, f of c is less than mu, and f of c is greater than mu. So there are three possibilities. F of c is less than mu, f of c is equal to mu, and f of c is greater than mu. This possibility is also there. Let's try to understand. The proof is very similar actually. So notice what happens in this case. There is mu and there is f of c here. Again, we choose a same kind of epsilon. This time, how should epsilon be? F of c plus epsilon should still be greater than mu. That's how we choose an epsilon. Okay. In other words, epsilon should be greater than, epsilon should be, let's try to see it. Epsilon is greater than mu minus, oh no, sorry, there's some issue here.
FC minus epsilon should be greater than mu.
Yes, absolutely. Yes, you are right. F of c, this is f of c minus epsilon. This is f of c minus epsilon. This is f of c plus epsilon. Correct. Very good. This is f of c plus epsilon. So we want f of c minus epsilon to be greater than mu. In other words, we want epsilon to be less than f of c minus mu. In particular, we can take epsilon is equal to f of c minus mu whole divided by 2. This can be a particular example of epsilon that you can take. If you take such an epsilon, then again you will use the same thing. There exists some delta greater than 0 such that mod of x minus c is less than delta implies that mod of f of x minus f of c is also less than epsilon. In other words, f of x lies between f of c plus epsilon and f of c minus epsilon. Okay, and notice that we have assumed that f of c minus epsilon is greater than mu. So we again got that whenever this condition is satisfied, f of x is greater than mu. So now we have to take a d, right? What d do we take? We take a d as follows. What is the d that we should take? We should take x minus delta by, c minus delta by 2. Okay, take d to be equal to c minus delta by 2 as before. This is strictly less than c. Okay, this is strictly less than c. And notice that mod of x minus mod of d minus c is equal to delta by 2, which
c plus delta by 2 it should be.
No,
here also.
No, it's minus only. So d minus, see, the thing is d minus c, mod of d minus c is also less than delta by 2. Why? Because what is mod of is equal to delta by 2? Why? Because d is equal to c minus delta by 2, right? So we are taking c minus delta by 2 minus c, and we are taking mod of that. This is equal to minus delta by 2 mod of that. Correct?
No. I mean, with this is smaller than c, so we will not arrive at any contradiction. C is the suprema.
No. Here we are actually coming up with the contradiction for something else. Okay, I will come to that. Right. Okay. So what we are coming up with the contradiction is we are finding. Just a minute. What are we doing here? Let's try to understand this clearly. Here we are trying to do something else. We are trying to say that. Oh no, sorry. What am I saying? Just give me a minute. We want to. This time we will not contradict that it is an LUV. We will actually contradict that it's an upper bound. So that's the kind of thing we should do. Just give me 1 minute. Just 1 minute. F of c is less than mu. This implies that f of t is, in fact, actually there is something. No. Actually, we should do something else. Notice that. Sorry. I don't know why I should have. In fact, notice something. Notice something that if suppose x belongs to, okay, now I got everything. If suppose x belongs to d comma c, okay, if x belongs to d comma c, then f of x is, what is f of x? F of x is greater than mu, right? So if x belongs to d comma c, then f of x is greater than mu. Yes. So what is happening is that d itself is an upper bound for C, for S. So D itself is an upper bound for S. Why? Because we know that C is an upper bound for S. First of all, notice that C is an upper bound for S. So any number, if suppose no number greater than C, if you take an x greater than C, if x is greater than C, then f of x cannot be less than mu. That we know. Implies f of x is not less than mu. That we already know. But if a number is between D and C also, f of x cannot be less than mu. Right? If the number is between D and C also, f of x cannot be less than mu. Therefore, if a number is greater than D, then f of x cannot be less than mu. Therefore, D is an upper bound for us.
Contradiction to C is least upper bound because D is smaller than.
No, it's not. We don't know whether it's least upper bound, but it's an upper bound. Okay, it's an upper bound. So we have concluded that D is an upper bound, and that contradicts the assumption that C is the least upper bound because D is smaller than C. So it contradicts our assumption that C is the least upper bound. This again is actually something that you will keep seeing. There will be two cases. In one case, whatever we do, the contradiction is for being the least, and the other case, it will be the contradiction will be for upper bound. So you will see this idea being repeated so many times in all proofs. You will use trichotomy, split it into three cases. In one of the cases cannot happen because it contradicts the fact that it's a least upper bound. The other will contradict that it's an upper bound. So that's what is happening. So the first case 2, we are actually in case 2, what we are contradicting, we are saying that C is not an upper bound. You can find a greater number for which also f of d is less than mu. So C is not an upper bound is what we are showing. In case 3, we are not showing that C is not an upper bound. C is perhaps an upper bound, but we can find a smaller upper bound. Therefore, C is not least among all upper bounds. So there are two different kinds of contradictions that we are getting. This again is a feature that is repeated in so many different proofs. Every proof that you see will, lot of proofs use this technique. So I think that those kind of things, if you emphasize, like, okay, this, so again, I don't know, like maybe I'm talking in the sense of how to teach is perhaps what I am more focusing on in some sense, like how I would teach. I'm not saying how to teach, maybe that's too arrogant to say that, but how I would teach when I'm teaching. So that's what I'm trying to say. I would emphasize on these factors, and I believe that students will find it easier when I emphasize these things. So I'm just sharing that. So yeah, sorry.
To prove the set of all x in Q such that x square is strictly less than 2, it will follow
exactly. Exactly. You use the same thing there. There are three, you use trichotomy, either the supremum is exact same theorem you use. And it's also real induction that we are using in that. So there are so many results. I'm very glad that you pointed it out. So the irrationality of root 2 is another example where the same proof technique is used. Exact same proof technique. So when we understand this and when we call it a name, I believe it becomes a lot easier. So that for me, that is, I think, the main thing that I wanted to share in some sense. Okay. So now there is a second question, right? So it's actually 8:10, but can I take a little bit more time, maybe 5-10 minutes? Is that okay? Because I said there are two questions. I couldn't talk about the second question at all. Or should I talk it the next time?
Yeah, maybe 2-3 minutes. I mean, I'm okay.
It's not really 2-3 minutes. So let me just throw it to you.
Yeah,
okay?
sure.
Let's just start it and maybe let's not complete it. Let me just say a few things. So again, so we have answered one of the questions, right? How do we know this? That's a question that we answered. But now the question is that, okay, so now we know that continuity is a stronger condition than IVP. If you are restricting our attention to these kind of domains. If you are restricting our attention to these kind of domains, then continuity is stronger than IVP. But the only example of a function that satisfies IVP that does not satisfy continuity so far all uses sine 1 by x. Right? All the examples we saw so far uses sine 1 by x somehow. So it's natural to ask, is sine 1 by x the only such function? Or are there other functions that does not satisfy IVP but satisfies continuity? It's natural to ask this question, right? What do you think? Is sine 1 by x really special? Or is there something else going on?
Similar periodic functions will also behave the same way.
Which functions?
Periodic functions. Similar periodic functions. Like
periodic functions, okay.
Not periodic functions.
Periodic functions, okay. Periodic functions satisfy this. Periodicity is kind of used there. Periodicity is kind of used. But it's also more than periodic, right? If suppose, how do I say? Yeah, actually you are correct. You are correct. Any periodic function, if suppose it has some value near 0, yes, then yeah, that's a wonderful point. So if you take a periodic function, then you can create, if f is periodic and f is defined on in the whole of real line. Okay, so that's the statement. Let's try to understand this. If f is periodic, okay, let me write it better. F from R to R is periodic. Then g of x is equal to f of 1 by x if x is equal to 0 and 0 if x is equal to okay, now here is where you have a trickiness. It should just not be periodic. It should okay, it's not enough that, okay, so C, if x is equal to 0, such that C is equal to f of A for some A in R. That's important. Then this function satisfies IVP. So that's a good point. That's actually a very, very nice point. So periodicity is one way of understanding this. Thanks for sharing this. I had not actually thought about it, but that's a very important point. Yes. If suppose C is in the image, then you can define the value at 0 to be that, and then it will still satisfy the intermediate value property. So that's maybe one answer. What more can you say? So now we have a huge class of functions, right? So periodic functions is a huge class of functions. Is this the biggest class of functions that you can come up with? Can you come up with more general functions and so on? So periodic is not like, so again, one of the things that I would like is, if suppose that set is a strict superset of continuous, that is better for us. If like not every periodic functions are continuous, right? There can be a discontinuous periodic function, for instance, right? This is an example of a discontinuous periodic function. Let's try to draw an example of a discontinuous periodic function. This is an example of a discontinuous periodic function, right? So there can be discontinuous periodic function. If the second category is kind of includes the first category, then we know that it's clearly a generalization. Can you come up with something like that is the kind of question that I was actually trying to ask. But thanks a lot for telling this example. This example is very, very helpful. So, and the thing is, that's one of the things that I wanted to talk about, but unfortunately I'm out of time. There is a bigger class. It's sin 1 by x is not really that special. There is a larger class of functions which also satisfy IVP, and that's what I wanted to talk about. Let me just state the theorem, okay, and stop there. So the theorem is called Darboux theorem. What does it say? It says that if f from AB to R is, sorry, let me not write it like this. If f from R to R is differentiable, okay, let me not write it like this either. If f from AB to R is differentiable on closed interval AB, then it satisfies IVP. Maybe I have to avoid some unnecessary technical complications. Let me just define it like this. The function is defined on a slightly bigger neighborhood. So f is a function from a minus epsilon to b plus epsilon to r, and it's differentiable on closed interval AB, then it will satisfy the IVP. So now notice something. Okay, I'm not going to go to the proof of this, but notice something. This is a strict generalization. So then f dash satisfies IVP. Of course, f satisfies IVP is trivial. Why is f satisfies IVP trivial?
Differentiability implies continuity.
Exactly. F satisfies IVP is trivial because differentiability implies continuity. Continuous function satisfies IVP, so differentiable function satisfies IVP. The stronger thing is if f is differentiable, then f dash satisfies IVP. That's the stronger statement. And all continuous functions are functions of this type. Why? Because of fundamental theorem of calculus. Because of fundamental theorem of calculus, every function, so if every continuous function is a derivative of something else, right? So if suppose we have a function f from AB to R, which is continuous, then we know that f is equal to capital F dash, where capital F is equal to integral from a to x, f of x dx. Right? So every continuous function is the derivative of some function. So therefore, this is a strictly bigger class. All continuous functions are included in these functions. All continuous functions are the derivative of something. That is what the fundamental theorem of calculus is telling us. So in some sense, this is a strictly bigger class. Again, the inquiry does not stop here. Can we look at an example of a function that is not the derivative of any function but still satisfies IVP? That is an interesting question. And I'm not going to answer that, but I just want to pick some curiosity. That's what I wanted to do. So I think I will stop here. Any questions, any comments? Was it interesting? Did it help? Anything from, I think I would like to hear. I can see a love sign. Thanks.
Yeah, certainly very interesting, sir, because I never thought of IVP this way. Really interesting. Yeah. Thank you so much.
Thank you. I'm glad. Like, I think, see, we are all fellow teachers. I think we are all trying our best to see how to communicate these things best to our students. So I think our issues will be very similar to each other. We're all facing this. It's not easy, right? Teaching these things are not easy at all. So sometimes we get some ideas and then we share it with others. Maybe it helps others. So yeah, that's mainly what that's how I am looking at it, to be very frank. So
I think it's that we always have IVP go as an after continuity comes IVP, and it's all about proving it. It's always treated post continuity. That's why we miss all this interesting and exciting things that that we were discussing last 2 days.
Even in tomorrow's session, tomorrow there is a session where you are going to do some problems, right? So even to tomorrow's session, you will be doing some things related to IVP only, like they will be related. So some of the things I casually remarked are there in the problem set. Like, for example, if a function has jump discontinuities, then it satisfies IVP, for instance. So, okay, which board are you using? So I'm using this app called Good Notes. So I don't know. So this is not okay. If your question is which tablet are you using, I'm using an iPad. So I'm not using say a graphical tablet that you connect to your computer. Okay, I'm using a separate device. So if you can see, if you browse, there will be two Divakarans here. So one I'm just sitting like this. There's just my photo, and one you have my video also. So I've signed in from two devices and I'm writing in my iPad. Okay. There are also some people connect their like just a tablet which they connect to their computer and then write. I'm not doing that. I'm doing something different. In iPad, I'm using an app called Good Notes. So Good Notes and Notability seems to be the most popular apps for writing in iPad. But again, these are not necessary. There are so many different options, whichever you prefer. So tablets, I think there are many. I think XPen is something that a lot of my colleagues use. So XPen is something like it's a tablet that you connect to your computer, and then when you write on the tablet, it's on the computer. So that many of my colleagues use that. If that is your question, that also I guess might be. So XPen is something they all use. So of course, like the most fancy one in that kind of tablets is something called Wacom, but they are very expensive in general. But it's mainly meant for artists actually. So thank you for all the kind words. I am happy to be of some use. Again, I will see you all on Thursday again. I will be spending some more time, 2 more hours with you. Yeah, that time I want to actually spend some time on something other than continuity, maybe integration or something like that. Okay, so that's the plan that I have. Okay.
Yeah. So thank you, Divakar. Yeah. So yeah. So we will close the session for today. Yeah. We will see all of you tomorrow. Yeah. Good night, everyone.
Good night. Good night. Yeah. Bye.
this Divakar, this GoodNote is free, is it, or it has